Okay, let's continue on with problem 5.90. If you remember correctly, we finished last time by calculating the contribution due to work, or the shaft work contributed by the flow crossing the inlet boundary, which in our case was boundary 1. And now we're going to calculate the portion due to boundary 2, the outlet. So we have our outlet. Here we know that the relative flow W is coming out at 120 degrees from tangential, and we know everything else about the geometry of the flow. So this one is a pretty straightforward application of doing our integrals for torque. But just to be clear, we're going to draw some vector triangles here. And so here's our outlet. And r hat still points outward. And theta hat still points in the counterclockwise direction. And we can draw some vector triangles. So we know that that W coming out, that this angle here is 120 degrees. I'm just going to write this one here being 60 degrees. We know that U is going this way because our device is spinning in a clockwise direction. And so we know that V, which is U plus W, is going to be somewhere, well, that's not a particularly good drawing now, is it? It's going to be somewhere like this. We know that the volumetric flow rate, when we do the integral over the area, is going to be equal to 2 pi r2, the radius, b, the thickness, times minus WR. And I write this as a minus because WR is in the negative r hat direction. Sorry, W is in the negative r hat direction. And so WR is going to be a negative number, and we always want Q to be a positive number when we do these problems. So that means that WR is equal to minus Q over 2 pi R2B, which from before was, let's see, 20 cubic feet per second. Divide that by 2. Divide that by pi. R2 is 2 feet, so we divide by that. And B was, what was it? It was about 0.08, 0.08 something or other. So let me see here. I think I have it stored. Whoops, no, I don't have it stored there. Yes, I did have it stored there. So I get, sorry about that, I get minus 19.30